Okay, 15 context-free grammar problems, let's go. Aha! Okay, so let's make a context-free grammar for this language, which is the set of all strings of the form a to the n, b to the n, which means that we have an equal number of a's and b's. Whenever we think about a context-free grammar problem, we need to think of two things, the base case and the recursive case. So here, the base case is when n is equal to 0, the smallest possible n for which a string like this exists. Well, that's just the empty string. So if we start making our grammar, we need a variable, and we need to generate the empty string, obviously, because that is the base case. But we now need to think about the recursive case. Well, the recursive case says we have an equal number of a's and b's, and all the a's come before all of the b's. So therefore, if we have some string that is not the empty string, that means that there is an a in there somewhere, and therefore it needs to be in the first half. Consequently, there must be a b in the second half. Well, if we generate an a at the beginning and a b at the end, the thing in the middle, since we're popping off, in some sense, one a at the beginning, one b at the end, therefore the thing in the middle must be another string of the form a to now n-1 and b to the n-1, same form. So therefore, if s, by assumption, makes all the strings of this form, therefore, we need to recursively call s in the middle here. And so we make the rule, s goes to a, s, b. So we make an a at the beginning, make a b at the end. So let's do an example. If we have n is equal to 10, then what we can do to generate that string is to apply this rule 10 times, making 10 a's at the beginning, 10 b's at the end, and then finally conclude by changing that one s into the empty string. And so therefore, this is a quick and easy grammar for the set of all strings of the form a to the n, b to the n. Okay, let's make a context-free grammar for this language, which is the set of all strings of the form a to the n, b to the m, where n is at least m. In fact, is bigger than m. So therefore, if we want to make a string in this language, we need to make an equal number of a's and b's, and then add at least one more a at the beginning. In fact, we can add many more. So let's make a grammar for the set of strings where they have an equal number, and then we deal with having to add more a's. So for every context-free grammar problem, we need to think about the base case and the recursive case. So the base case here is going to be at least one a, because we need to satisfy this condition. So we need to make some variable that spits off one or more a's. And that's going to be, I'm going to call it x. And the base case for that, at least one a, is a single a. And if we want more, we can obviously just add another rule where we can make more a's if possible. So this variable x makes all strings that have at least one a. Now, we need to deal with the recursive case here, which means that we need to match b's with a's. So every b has one a with it, and there are potentially, in fact there are, more a's than b's. So let's spit off an equal number of a's and b's right here. So at this point, we have an equal number, and then once we're done spouting off the b's, we need to go over to the a's and then make some more a's, because that's what x does. So the base case here for s is going to be the x variable, because that spits off one or more a's, and we need that. So the base case for s is the variable x right here. So why does this work? So suppose that we have a to the 5 and b to the 3. So the number of a's is more than the number of b's, so we're good there. How does this grammar make a string like this? Well, it's got to match 3 b's with 3 a's, because, so notice here that each of the b's is going to match with one of the a's, and there are 2 more a's than there are b's. Well, how does the grammar make this string? It applies this rule 3 times in order to make 3 b's and then 3 a's. And then the x variable, which is going to live in the middle right here, is going to spout off more a's. In fact, in this case, it's going to spout off 2 more. So this is a quick and easy grammar for all the strings of the form a to the n, b to the m, where n is bigger than m. Okay, let's make a context-free grammar for this language, which is the set of all strings of the form a to the n, b to the m, different letter, a to the n, where n and m are both at least 0. So notice here that the only dependencies between these runs, this set of a's here, this set of b's here, and this set of a's here, is that they start and end with the same number of a's. But the number of b's is some other letter, and there's no relationship between n and m here. So therefore, we need to think about the base case and recursive cases since we are making a context-free grammar. So the base case here is this set of b's right here, which can be any number of b's that we want, at least 0, because it says here m is at least 0. So let's make a variable for that. I'm going to call it capital B, and that's going to make 0 or more b's. Well, the base case for that is the empty string, 0 b's. And if we want more b's, we can just have a rule like this, which spouts off a b and then recursively calls the capital B variable. Okay, well then how are we going to incorporate the a's here? Well, if we spout off all the a's, we need to, as the base case for that, so to speak, come down to this variable b, which spouts off all the little b's. So I'm going to make a variable s, which is going to recursively just make one a at the beginning, one a at the end, because they have to match up. Any number of them, though, because it's at least 0. So that'll be a, s, a. So spout off one a here, spout off an a at the end. And then the base case for that is this variable capital. And so therefore, this is a quick and easy context-free grammar for the set of all strings a to the n, b to the m, a to the n, where n and m are at least 0. Okay, let's make a context-free grammar for this language, which is the set of all strings a to the I, b to the j, c to the k, where I plus j is equal to k. So here, the number of a's plus the number of b's is equal to the number of c's. There's no more c's than that, there's no fewer. It's exactly the same as the number of a's plus the number of b's. So therefore, we need to somehow relate each a that we make here with a single c over here, and every b that we make with a single c also. So let's go ahead and get started. Well, what is the base case? Well, the base case is the empty string, because if the number of a's is 0, number of b's is 0, number of c's is 0, then that equation works. 0 plus 0 equals 0. So we need the empty string right here. Well, let's think. Well, if we are going to generate some a's and then c's, one thing that we might try is something like this. ASC, every a matches with every c, and then do the same thing with the b's. Every b that's made matches up with a c. And this seems reasonable until you notice the fact that we can apply these rules independently of each other. We can apply this one, and then this call to S could then call the B one, which then calls the A one. So we could have some mix and match right here. But the language right here says that all the A's come first, then all the B's, and then obviously the C's. So the way that we can think about this is that since the A's are at the beginning, what we can do is do all the A work first, and then once we're done, switch to a different variable, which makes all of the b's, and then we're done at that point. So instead of doing this, let's switch over to a different variable. Let's call it x. And then x is going to do the similar thing, but for the b's. So let's do bxc, or empty. So at that point, we've matched some number of a's with number of c's, but once we're done with the a's, the number of b's must match the number of c's that need to be made. And so we have a very simple grammar that matches the number of b's with number of c's, and we marry that up with doing the a stuff up here with the s variable. And so therefore, this is a quick and easy grammar for a to the I, b to the j, c to the k, where I plus j is equal to k. Okay, let's make a context-free grammar for this language, which is the set of all strings a to the I, b to the j, c to the k, where the number of a's, which is I here, plus the number of c's, which is k here, is equal to the number of b's. So you can actually rewrite this language as I plus k in terms of the exponent for b, the number of b's. So if you think about this, you can rewrite the string as a to the I, b to the I, b to the k, c to the k. In some sense, we can split that up into IBs and then another KBs, which are going to match up with the C's, and the beginning set of B's are going to match up with the A's. So we can think of this in terms of two different equality problems. Have this one and then this one, and they are concatenated together. So we can think of a solution to this by having a variable s make two variables where one of them is going to make this, and the other one is going to make this, and then concatenate them together. So let's call them A and B. So A is going to do all the work of this guy, and that's fairly simple. It's just the number of A's matches the number of B's. So that's going to be little a, little b, and the base case for that is empty. And the base case for that, of course, is empty. And over here for capital B, we can do a similar scenario. So capital B goes to little b, little c, or empty. So the fact that we can split this up in some sense, even though it's not really splitting it up, allows us to make two different variables to handle the two separate problems, so to speak, completely separately, and then concatenate them together. So therefore, this is a quick and easy grammar for the set of all strings of the form a to the I, b to the was j, now is I plus k, c to the k, and if this was j, it would be that I plus k is equal to j. Okay, let's make a context-free grammar for this language, which is the set of all strings that are not of the form a to the n, b to the n. So for example, one string might be ba, because it has a b before an a. Another example might be we have two a's and then a single b, because it doesn't have an equal number of a's and b's. Because we're looking for a set of strings that are not of this form, which are equal a, equal b, and then a's go before b's. So let's think about how we can solve this. One way we can think about this is, if there's a b before an a, then it's automatically a string in here. Doesn't matter what it looks like. Any string at all that has a b and then an a after it immediately is not of this form. So we can split it up into different cases. So let's make a variable s, which is going to have a variable, let's call it a, which is going to handle this. And I'm going to add more to variable s here. So a is going to handle any string that has ba in it somewhere. Well, the way we can do that is by saying, is a capital A or b capital A? At some point, there's going to be a ba in there somewhere. So let's allow ourselves to spit off as many a's or b's at the front and at the end as we want. And the base case is going to be BA, because that's the thing that we're targeting. And so therefore, let's add some more rules. Capital A, little b, and then the base case is going to be little b, little a. And so capital A is going to make every possible string that contains a BA in it, because this is the base case. And these four rules right here allow us to do whatever we want on the left and whatever we want on the right. Okay, well, what are we going to do in the other case? Well, what is the other possible case? The other case is when these two numbers, where the a's do come before the b's, but the counts don't match up. Okay, so for instance, if we have a string like this, we can have a bunch more b's than a's, that's allowed. As long as they're not the same number, then that's all that we want. So what we can do is, we can phrase this as some number of a's, some number of b's, where they're not equal. And whenever you have a not equal problem, you can turn that into one is less than the other one, or the other way around. So for instance, if it is some number of a's, which is I, so if the number of a's is I, and the number of b's is j, then as long as I is not equal to j, we're good. So we can split that into I is strictly less than j, or Boolean or, j is less than k. So let's handle each of those separately. So I'm going to have a variable b sub I less than j. So this is going to handle the case where there are fewer a's than b's. So what that means is that every a is going to match with a b, and there are some more b's, at least one more. So let's go ahead and match those up. So little a, little b, and then capital B I sub. So this rule right here is going to make an equal number of a's and b's, but we want the base case to handle making at least one more b. So let's make a variable just for that called x sub b, and that's going to be the base case here. So here, the base case for this is going to be a single b, but we can allow ourselves to make more. So x sub b, and then the actual character b. Notice the subscript is just part of the name. So that will allow us to make an equal number of a's and b's, and then as the base case, make at least one more b. So that handles this case. So we need to add a rule up here that says either we have a b before an a, which is what this variable is right here doing, or we have that I is less than j, so we have that. Or it's the case that the other way is true, that I is bigger than j. So I bigger than j. It's getting a little crowded up here. So let's make a variable for that, I bigger than j. So making this variable, we need to have an equal number of a's and b's, and then spout off at least one more a. So let's do the similar thing that we did up here. And we got to be sure that we're referencing the right variable right here. So notice it says I bigger than j here, b. Or, and then now I need to spout off more a's. So I need to make a variable that spouts off more a's. So x sub a goes to little a, or x sub a. Okay, so now we have treated every possible case. It is either the case that there is a BA somewhere in there, or if there isn't, then the number of A's is less than the number of B's, or the number of A's is bigger than the number of B's. So this is a context-free grammar for the set of all strings that are not of the form A to the n, B to the n. Okay, let's make a context-free grammar for the set of all strings that are not of the form A to the n, B to the n, C to the n. So the uncomplemented version of this language is not context-free, but this one is because we're going to make a context-free grammar for it. Well, if a string is not of this form, then there are several conditions in which it could be. For instance, if it has a BA in the string somewhere, then that is not of the form A to the n, B to the n, C to the n, because that requires A's before B's before C's. So if it contains a BA anywhere, then we're good to go. If it contains a CA anywhere, we're good to go. And if it contains a CB anywhere, we're good to go. So let's go ahead and make those. I'm going to have a variable x sub BA handle that there is a BA somewhere in there. Whatever the string looks like, wherever the BA is on either side, then anything, literally anything, can appear on either side of this BA. So let's allow ourselves to spit off as many A's and B's on either side as we want. And in fact, C's here too. So let's do A x sub BA, or B x sub BA, or C x sub BA, or X BA, and then so the A can be generated at the end, or XBAB, or XBAC. And then finally, the base case is going to be BA, the forbidden string that we were hunting for, so to speak. So then now we could, in principle, do the exact same thing for CA and do a similar type thing. And of course, we need to do a similar thing for CB. So I'm not going to write these down, but I'm assuming that these three variables exist. Well, the other way that a string could be not of this form is if it doesn't fit one of these buckets, it must have A's before B's before C's, but one of the counts is off. So it either is the case that we have A to the I, B to the J, C to the K, where I is not equal to J, or J is not equal to K, or I is not equal to K. So let's handle one of them, and in principle, we could do the other two. So let's call it A sub I not equal to J. Well, if two counts aren't the same, we can solve that by saying one is less than the other one, and then union the two cases. So I is less than J, or I is bigger than J. So let's make two variables for those. So AI bigger than J, or AI is less than J. So then let's do the first one. So AI bigger than J. What that means is that we have more A's than B's, but then the number of C's, I don't care, as long as the number of A's is bigger than the number of B's. So notice that we need to have an equal number of A's and B's and then have more A's on top of that. So let's spout off an equal number to start with, I bigger than J, B. And then we need to have another variable be able to handle adding more A's than that. So let's call it X sub A, allowing ourselves to make more a's. And x of a is going to have a base case of a single a, or allowing ourselves to make more a's. But this is not quite the solution, because right here we're saying that this b is at the very end of the whole string, but that's not the case. We're allowing ourselves to have some c's at the end of that. So the way to fix that is to not do this, but instead have another variable where this ai bigger than j thing is going to spout off some c's, any number, and then as the base case, go to that other variable that does the thing that we just did. So let's allow ourselves to make as many c's as we want at the end specifically, because that's where the c's are. So that allows us to make as many of those as we want, a bunch of c's at the end. But as the base case, we need to go to a different variable. Let's call it I bigger than j, comma 2. And then that one is going to do the work that we just did. So let's go ahead and write that down. So I bigger than j 2 with a b at the end. And then go to the xa variable that we just did, which spouts off one or more a's. So that handles this one. This one is incredibly similar in that we will do the same trick we had here of spouting off some c's at the end, but then the base case would be a variable of the form x sub b, which is going to spout off one or more b's. And then the other two cases are incredibly similar. The only different one is I not equal to k, because there, the one which doesn't really matter in terms of count is in the middle. And so therefore, we would need to split it off into having the base case being make as many b's as you want. And instead of having to do this, you have to rearrange the variables somewhat. But I argue that it's not that much different from this. So that was a context-free grammar for the set of all strings that are not of the form a to the n, b to the n, c to the n. Okay, let's make a context-free grammar for this language, which is the set of all strings of the form a to the n, b to the n, c to the m, d to the m. Notice that it's a different variable for these two segments, basically, m here and n here. But as long as we have an equal number of c's and d's and an equal number of a's and b's, the counts otherwise don't really matter. So we can think of this as two separate equality checks. We need to have these two being the same number and these two being the same number. So let's think about how we would do that. I'm going to make a variable capital A, which is going to do this one. So that's going to be A, capital A, little b, or empty. That's the base case. This is the recursive case. And then another variable capital B, which is going to do this second half, which is going to be C, capital B, D, or epsilon. So here we have an equal number of C's and D's, that's what B does, and an equal number of A's and B's, that's what A does. But these two subproblems are combined by concatenating them together. So my start variable needs to concatenate whatever this capital A variable does and whatever this variable capital B does. So concatenate them like this. So that was a quick and easy context-free grammar for all the strings of the form A to the n, B to the n, C to the m, D to the m. Okay, let's make a context-free grammar for this language, which is the set of all strings A to the n, B to the m, C to the p, where n is at least m, or m is equal to p. So in other words, it is either the case that the number of a's is at least the number of b's, or, and it could be false under the second condition, the number of b's is equal to the number of c's. So we can think of this as two independent problems that are connected by or. And when that's the case, let's use union between the two subproblems. Let's solve the first one, and then union the solution for the second one. So let's do the first one. I'm going to make a variable called n at least m, so that we know which one we're doing. Well, that means that the number of c's here does not matter, because that doesn't factor into this subproblem right here. Only the number of a's and number of b's matter. So that means we can spout off as many c's as we want. So let's go ahead and do that. What we can do is recursively call the variable a sub n at least m, and spout off these c's at the very end, because that's where the c's are in the string. But the base case is when we're handling just the a's and b's, because again, we can have as many c's as we want. So let's make a variable called x1. I'm going to call it x1. Well, what is this x1 variable going to do? Well, if the number of a's is at least the number of b's, then that means we need to make as many a's as b's, but have some more a's potentially. So let's make an equal number, and that's what this one is doing right here. But as the base case, we need to spout off potentially more a's. So one thing that you might try, and it does work, is something like this. The base case, the true base case, is when you have nothing left to generate, which means that we could have an equal number, but if we spouted off some more a's at the beginning, then that's good. We're allowed to make more a's. But at some point, we got to make this variable go away, and one way is with the empty string. Okay, so that handles this one. Let's handle m equals p. So similarly to this previous one, the number of a's for this case does not matter. So let's go ahead and have this variable just spit off as many a's as we want at the beginning. We need to recursively call this variable by spouting off an a at the beginning and then recursively calling it. So that will look like this. And then once we're done those, now we're focused on the number of b's and c's. And so let's transfer to a different variable called x2, which is going to do precisely that. So x2 is going to make an equal number of b's and c's. So that's very easy to do. We did something similar up here. And then the base case here, because we need it to be equal, needs to only be empty. Whereas here, we needed to generate some more a's potentially if we needed to. But we can have an equal number. Here we need to have an equal number. Okay, so we have a variable that does the first condition, another one that does the second condition. How do we combine them? With this or, which is vertical bar. So my start variable is going to be this variable, a n at least m, or this other one. So therefore, this is a context-free grammar for the set of all strings of the form a to the n, b to the m, c to the p, where n is at least m, or m equals p. Okay, let's make a context-free grammar for this language, which is the set of all strings of the form a to the I, b to the j, c to the k, where I is equal to j, which means we have an equal number of a's and b's, or we have an equal number of b's and c's. This language is actually pretty famous because no matter what grammar you make for it, provably, the grammar must be ambiguous. So we're not going to try to avoid ambiguity here because it's impossible. Okay, so how do we start this? Well, notice that we have two subproblems that are basically equal to each other in some sense. It's just two different equality problems combined with an or in between. Let's solve the two subproblems and then combine them using or. So let's make a variable ai equals j. So this variable is going to handle when the number of a's equals the number of b's. Notice here that the number of c's for this does not matter at all. So we need to spout off as many c's as we need to before we tackle the actual problem of equal a equal b. So notice also that the c's need to be generated at the end. So I'm going to recursively call this variable and then spout off the c at the end. And then once we're done, we need to start generating an equal number of a's and b's. And that's pretty easy to do, but we need to transfer to a different variable. So I'm going to call it x1. So x1 is going to make an equal number of a's and b's, and that's all it does. So a, x1, b, or empty. So that's pretty easy. For j equals k, we can do a similar thing, but we need to generate the a's at the beginning, not the end. So let's do a similar thing to this, but we got to reference this variable and not this one. So little a, capital A, sub j equals k, that's referencing this variable. And then once we're done, we need to switch to a different variable which makes an equal number of b's and c's. We can't use this one because that involves a's and b's. So I got to use another variable, x2, which is going to spout those off. And that's pretty easy to do because it's just like this one. All right, so that handles j equals k. We have I equals j done. How do we combine them? Using or, because that's what the language asks for. So let's make a variable s, which does this one or this one. I equals j, or j equals k. And that is a fairly easy context-free grammar for the set of all strings of the form a to the I, b to the j, c to the k, where I is equal to j, or j equals k. Okay, let's make a context-free grammar for this language, which is the set of all strings of the form a to the n, b to the m, c to the m, d to the n. And notice that there's no relationship between m and n here, but the m's are in the middle, whereas the n's are on the outside. So you can think of this in terms of two equality problems, but they're kind of nested in each other. So the n equality problem is on the outsides, and the m problem is on the inside. So we can think of solving this by thinking about how these two have to be the same. So let's make a variable specifically for those. So I'm going to call that x. And that is going to make an equal number of b's and c's, where the b's have to come before the c's. But then how do we handle this? Well, once we have made an equal number of a's and d's, at some point, once we're done making those, the stuff in the middle is what this variable x makes. So let's do a similar thing to this, where we do it for a and d, but the base case is, once we're done doing this, is what this variable is. So let's make a variable s that will spit off an a and a d on both sides, and then its base case is going to be this variable x, which does the b equals c problem. So that was a fairly easy context-free grammar for the set of all strings of the form a to the n, b to the m, c to the m, d to the n, where they're both at least 0. Okay, let's make a context-free grammar for this language, which is the set of all strings that have an equal number of a's and b's. This seems rather easy, but notice that it doesn't specify where the a's and b's are. Are they at the end or at the beginning? Doesn't matter, they can be interspersed. As long as they have an equal number, it doesn't matter where they are. So for instance, we can have b, a, b, b, a, b, a, something like that. So there are 4 a's here and 4 b's, and so therefore our grammar, whatever we do, should have an ability to make a string like this, as well as every other string with an equal number of a's and b's. Every context-free grammar problem can be phrased in terms of base case and recursive case. The base case here is pretty easily seen to be the empty string, because it has an equal number of a's and b's. So let's suppose that there's an a somewhere. So in the string, there's an a somewhere. I have no idea where, because the order, we have no idea. But that means that there's a b somewhere. It could be right next to it, it might be way over here, it might be over here. So let's handle those cases. So if there's a b over there, then that's fine as long as these segments in total have an equal number of a's and b's. And similarly, the b could come before the a. And again, as long as these 3 segments, before, middle, and after, have an equal number of a's and b's in total, we are good to go. So how should we think of this? Well, each of these segments can have an equal number of a's and b's, so each of these segments could be empty or not. So we can actually solve this problem by recursively calling these segments. Well, you might say, well, what if there's more a's over here, and then fewer a's right here? If we just recursively called the variable that we make in each of these segments, that would say that each of these has to have an equal number of a's and b's individually. According to this, as long as the number of a's and b's in total across these is the same, then we're good. The key is in the fact that context-free grammars are non-deterministic. So if there is any way to generate the string whatsoever, the context-free grammar will find it. And so therefore, each time we do this, as long as these are just recursive calls and that's it, and there's no other weird case in there, as long as we just do this, then no matter what, we generate an A and generate a B, and there's no way we can have some scenario where we have more A's than B's. That's how we solve the problem. So let's actually solve the problem. So let's make a variable s right here, and the base case, of course, is the empty string. But let's look at our little picture again. So if we have an A here and then a B somewhere after it, might be next to it or it might be way further, then that means that we recursively call S on each of these pieces. So SA, SB, S. And then similarly, if the B came first, then that means we need to do something like this. And then that is a quick and easy context-free grammar for the set of all strings that have an equal number of A's and B's. We can actually make this a little better though, because it turns out this grammar is ambiguous. Because it turns out there are some strings where you can apply this rule first and then make the string eventually. Or we can apply this rule first and then make the string eventually. So what we want to do instead is make this grammar unambiguous if possible. And the way we can do that is by noting that we can treat any A and any B that we want, including the very beginning. The beginning of a string must be an A or it must be a B, one of those two, as long as it's not the empty string. Well, if it's an A, there's a B out there somewhere, I have no idea where. And if it starts with a B, there's an A out there somewhere. Again, I have no idea where. This grammar is unambiguous because the beginning of the string cannot simultaneously be an A and a B. And so therefore, since we're not generating anything over here now, therefore, this grammar is unambiguous because we can't change these little a, little b to anything else. So therefore, this is now an unambiguous grammar for the set of all strings that have an equal number of a's and b's. Okay, let's make a context-free grammar for the set of all strings that have more a's than b's. Here, the number of a's can be really anything compared to the number of b's as long as it's bigger, and the a's can be placed anywhere we want, and the a's can be placed anywhere relative to the b's. They don't have to be all before or all after, they can be interspersed. So for instance, if we have A, B, something like that, we have 3 a's here and 2 b's, so our grammar should be able to make a string like this. So let's think, how are we going to think about this problem? No matter what, each of these b's in this string is matched up with some a somewhere. I'm going to have a start variable. It's going to make this, E, A, E. It might be the case that we have an A somewhere that is not matched by a B anywhere, but then there's another one way further away, and then there's another one way far away. It's not necessarily the case that the more A's than B's are right next to each other. But the way to solve this is to allow ourselves to do this, to call S and then call. So what we can do is to call S twice, where we have a segment that looks like this, and then another segment that looks like that. So this A right here, this capital A, is going to make a single A, and that's it. But we can recursively call S by allowing ourselves to have more and more and more of these segments to make more and more single A's that are not matched by a B. So let's go ahead and make these variables right here. So capital A, that's just going to make a single A, and that's it. In fact, we could even just replace that right here. And in fact, that's what I'm going to do. But capital E is going to make an equal number of A's and B's. And we know how to do that because that is the base case of empty, because that's equal number of A's and B's. And then A, E, B, E. So every A at the beginning must match some B somewhere. And then if it's a B at the beginning, it must match an A somewhere because it's an equal number. That's the problem that capital E is trying to solve. So to recap, this variable S is going to make a number of sections, at least one, because we have to have this at least. This allows us to make us more. But a number of sections where it has at least one more A, in fact, exactly one more A than the number of B's. This has an equal number, this has an equal number, and we add one here. But if we want more A's than B's than that, we just iteratively do this same thing until we're done. In fact, one other way we can solve this is to do this. We recursively call S right here and then terminate with one of these guys. That'd be an equivalent way of doing that. So we must have one of these, but we allow ourselves to have more if we want to. So that's a fairly complicated but still straightforward context-free grammar for the set of all strings that have more A's than B's. Okay, let's make a context-free grammar for any regular expression that we want. So in order to do so, we need to follow the rules of what a regular expression can look like, because we're saying here we can convert any regular expression into an equivalent context-free grammar. We need to appeal to the formal definition of regular expression, and there are 6 cases. It is either the empty set, so that's the first case. 2 is going to be just the empty string. 3 is just a single terminal, or a character if you want. 4 is going to be the union of 2 smaller regexes. 5 is going to be concatenation of 2 regexes. and then 6 is going to be the star of one regex. So let's make a context-free grammar for each one of them. For this one, it doesn't have any strings in it, so our grammar cannot generate any strings. If we write no rules down, it cannot generate strings. So we're already done. This one, on the other hand, we need to generate the empty string because that's the only string that's described by that regex. And this is easy enough to do, just convert the start variable into the empty string. And for a single letter, it's a similar story. We can have a variable s that goes to little f. Well, how do we do the union? Well, supposing that we make a context-free grammar for each one of these, then we can combine them using vertical bar, or. So if we have start variables s1 for this guy that recursively have been made for r1, and then s2 makes all the strings r2 can, we can make a context-free grammar for all of this with s1 or s2, assuming that s1 is corresponding to r1 and s2 with r2. To do the concatenation, it's a similar story. We can just concatenate this start variable with this one. So s1, s2. Just put them right next to each other. And then for star, that's a little trickier because we can have any number of calls to s1, but the base case is going to be the empty string in the case that we don't call r1 at all, because r1 star means 0 or more copies of r1. Well, the base case is 0, which is the empty string. So to make a context-free grammar for that, the base case is going to be empty string, or calling the start variable for this, which is s1, and then recursively calling ourselves, which is s. So that's a fairly easy, straightforward way to convert any regular expression into an equivalent context-free grammar. Okay, let's make a context-free grammar for the set of balanced parentheses. And what I mean by that is that if there's an opening paren, then that means that there's a corresponding right paren, but it appears on the right side of it. So something like that. So for instance, this string is not balanced because this character, the closing paren, doesn't have a matching opening paren to the left of it. Whereas if we consider this string now, then these left guys have a corresponding right one, and it appears after it. So how do we make the set of balanced parentheses? Well, we can have a nested structure like this, and we can go as far as we want to, but we can have ones like this. So it doesn't have to be that all of the lefts, the openings, have to go before all of the rights. It's just that each of the lefts have a corresponding right on the right side, so to speak. So how do we make a context-free grammar for this? So we need to think in terms of base case and recursive case. So the base case is going to be the empty string because there's no openings and there's no closings. So we have that base case down. That's pretty easy. But if the string is not the empty string, then that means that it must start with an opening paren. It can't start with a closing paren because that's not a balanced set of parentheses. So it must start with an opening paren, but then its closing one might be really far away. I have no idea where, because it might be that the closing paren is some very far off thing over here. I have no idea. But what has to be in the middle must be another set of balanced parentheses. So what has to go in here must be a set of balanced parentheses. But we can have a set of balanced parentheses with another set of balanced parentheses. So we can have s concatenated with s2. And so that would be a context-free grammar for the set of balanced parentheses. However, this grammar is ambiguous because of this rule right here. If we think about it, anytime we have a set of balanced parentheses, so like these ones right here, because we're assuming that they're balanced in here, then that means we can have a set of balanced parentheses after this closing one. So we can do this right here, where we have an s right here. And since now this rule doesn't generate anything, and this one generates something, therefore it's impossible for this grammar to be ambiguous. And so therefore this grammar is unambiguous. So that was a quick and easy context-free grammar for the set of balanced parentheses.